Huh?
Their quiz gonna look like.
Pull that, maybe pull that. Oh, that's for math team.
Math team, are you gonna work on the math competition? How do I do that work? So that's it. 1 year, the month of January had exactly 4 Mondays and exactly 4 Fridays. On what day of the week did January first fall on that year?
What does the
I like
what
peanut
math
butter.
contest
Everything up to pre-calc.
Huh?
everything up to pre.
What is?
Bro,
Math team contest is everything up to pre-calc. No calculus.
Wait, do you have a calculator?
Huh?
I don't calculate.
Do I have a calculator?
Like, he's asking if math contest has calculator.
Oh, some contests do. It depends on the contest. This one does. This one.
I think this one-
and then you'll be.
All right, guys, page 13. So we did this method yesterday. Today we're talking about washer method, and the only distinction is that there's going to be a gap or hole that we have to make sure we subtract out for certain objects so that we're able to provide an appropriate volume for that object. The way that we can tell is for this method, if you look at your shaded region, in relation to your axis of revolution, notice that your shaded region is completely up against your dotted line. There's no gaps, there's no holes. It's completely filled in. So as we rotate, our object is going to be a complete solid. There's no hole, there's no gap. So we don't have to worry about having to subtract something out. But let's say we have a shaded region that looks like a leaf that is kind of pointing in that 45-degree angle here. It's made up of two separate functions, and we're going to find the volume of this later. But look at how this is interacting with the axis of revolution. Okay, it is touching, but that's not the main thing. But it's the fact that you see how there's a gap. So the big thing is if you have a flat surface of your shaded region up against your dotted line, then it's going to be washer method. Sorry, this method. But if you have a curved region up against your axis, then there's always going to be some sort of a gap or hole. We have to make sure we subtract out. And so this is going to require washer method. Okay. And if we were to rotate this around our axis of revolution, it's going to end up giving us this bowl-shaped object with this hole in between. And we need to be thinking about, rather than thinking of this as adding up infinite numbers of cylindrical circular disks, we're now going to be adding infinitely many circular rings, which we call washers. Okay. Okay. So we're adding these infinitely thin circular rings, and all the rings have different widths to adjust for the shape that we're going to be creating. Draw this again here. Now let's just look at one representative ring here. If I were to ask you, if I have a circle within a circle, how can I go about finding the area of that ring or that area between the two circles? What would your formula be there? Or what information would you need to find the area of that? Yeah, radius of
Like the whole thing and just the inside.
right. So radius of the two circles, right? So I need to find the radius of the big circle, find the radius of the small circle, and then what would you do?
You would like subtract them,
Subtract the
the small one from the big one.
smaller what? What are we subtracting? The radius?
So volume.
Area, right. So let's say big R is the radius of the larger radius of the large circle, and little r is the radius of the small circle. Then it'll be pi big R squared minus pi little r squared. So this is basically what we're going to do with washer method. This will give us the two-dimensional circular ring that we're looking for, and then we'll add on that dx or dy to give it that third dimension. So before it was just pi big R squared dx. Now it's going to be pi big R squared minus pi little r squared dx. So that's the only distinction between disk method and washer method. Okay, so we'll do the easier problems first, which are the horizontal axis, which will produce vertical radius. And again, our radius is always going to be perpendicular to your axis of revolution. We're going to draw two radius, one big R and one little r. So to draw the big radius, we're going to start on the axis of revolution. That's going to be your dotted line. And you're going to, from your dotted line, you're going to extend a 90-degree angle away from that dotted line towards the outer or the further curve. That's going to be your big radius. And then you're going to draw the small radius. Small radius is going to be the portion you want to subtract out. Again, you're going to start on the dotted line, and then you're going to extend to the closer curve. That's going to be your little r. All right, so now we're going to do this problem here in more detail for example 1. Okay? Find the volume of the solid enclosed by the graph of y equals x squared and y equals square root of x rotating or revolving around the x-axis. So let's go ahead and draw our dotted line in. We're rotating about this line. And again, your dotted line is your center of your object. I know it doesn't seem like it because it looks like it's at the edge, but after the rotation, your dotted line, your axis will be the center of whatever object you're creating. Notice that you have a curved region up against the dotted line. The fact that it's touching is not that important. It's the fact that there's all this gap, right? So the only time you're going to have this method is if you have a flat surface up against your dotted line. If it's anything else up against the dotted line, there's always going to be a gap, and there's always going to be a washer method. Okay. So that's the first thing we need to be able to do is to be able to look at a diagram and recognize, wait, is this method or washer method? Okay, so washer method here. We need two radius. So always start on your dotted line, and we're going to extend to the curve that's further away. Okay, that's going to be now going to be your big radius. Again, start on the dotted line and extend to the closer curve, the curve that's closer, and that's going to be a little r. Okay. As long as you're putting your big radius and little radius next to each other, it should be always obvious which one is big R, which one is little r. Your big R is always going to be longer in length than little r. As long as you put them next to each other. If you put them far away from each other, then the graph may suddenly change in ways that causes little r to look larger than big R. So I would just always put them relatively close to each other. So you always have that visual connection. Okay, this is obviously big R because it's longer than little r. Okay, after that, we're going to build our two radius. Top minus bottom. The top of big R is sitting on the root x. The bottom is sitting at the 0. So it's going to be root x minus 0. Little radius. The top of little radius is sitting on the root x. Sorry, it's sitting on the x squared. Bottom is sitting at the 0. So x squared minus 0. Okay, so here's the formula above. So what we do here is to adapt this formula a little bit, we like to factor out the pi, and then we do big R squared minus little r squared. Right. Just so that we don't have to write pi so many times. So usually we factor the pi out. Integral big radius squared minus little radius squared dx. Okay, so this is our formula for washer method. Our bounds is also in terms of x. We want to find the furthest left and furthest right. The furthest right is the intersection between the two curves, which is occurring at x equals 1. So v is equal to pi, definite integral from 0 to 1, big radius squared minus little radius squared. Now, this is a fairly simple integral formula that you can just enter into your main line, but I just want to kind of show you how I like to do this, especially as your big R and little r gets messier and messier. I like to have my big R and little r stored under different y1 and y2. So under y1, I'll let y1 hold my big R, so square root of x. Under y2, I'll let it hold my little r, which is x squared. Then I'll go back to my home screen, Math 9, integral from 0 to 1. Big radius squared, so that's alpha trace y1, minus little radius squared, alpha trace y2. Yes. And if you have this set up, then you can just change your y1, y2 for future problems, and then just keep going back and just calling the same function and just adjust the bounds. That could save a little bit of time of entering a bunch of notations, especially if you have this already set up for washer method. So 0.3 converted into a fraction is 3/10. But 0.3 is fine because 0.3 is an exact value. So either 0.3 or 3/10 pi would be a good representation of your volume. Units cubed to indicate that we're finding something that is volume related, three-dimensional. Example 2. Find the volume of the solid created by revolving y equals x squared plus 1, bounded by the line y equals 2, rotating about the x-axis. So we have two graphs here. We have y equals x squared plus 1. That's a parabola with a y-intercept at 1. Y equals 2. So to close off this shaded region. We're rotating about the line y equals 0, x-axis. In this case, it's even more obvious that this is going to be washer method because the graph is not even touching. So we know that after this rotates, it's going to kind of create this weird ring-shaped object. But I want to keep reminding us that this is not the edge of the diagram. This is the center of the diagram. We're just not seeing the other portion that's that the graph is creating. So we know we have to draw two radius, one that extends from the axis to the furthest boundary. That'll be big R. And little r will extend from the axis to the closer boundary. We also need to find the boundaries because the boundaries, the intersections will act as our boundaries. We can do this by hand here. So we'll set x squared plus 1 equal to 2. We get x squared is equal to 1. So x equals plus or minus 1. Okay, let's build out our big radius and little radius. Big R is top minus bottom. The top of big radius is sitting on the 2. The bottom of big radius is sitting on the 0. Little radius, top of little radius is sitting on the curve. The curve is x squared plus 1. Minus the bottom of little radius is sitting on the 0. We have everything that we need to build out our volume by washer method. Big radius squared minus little radius squared dx. I'll have y1 hold my big radius. I'll have y2 hold my little radius. I'll just adapt my integral notation. I'll just go from -1 to 1. See if I can convert that to a fractional value. (64/15). Make sure you attach pi, cubic units. Any questions? Let me just point out two common mistakes that I see students make. One is that some students feel like there has to be a complete gap in order for it to be washer method. So then some students feel like, oh, it's touching, so that means there's no gap, and so they would want to do this method for this. So just make sure we understand that touching is not good enough. We need to be a flat surface up against a dotted line in order to be a disk method. If it's any other scenario, if it's a curved region touching, or if it's complete gap, it's gonna be washer method. So it is harder to create scenarios for disk method because you got to find a flat surface, and that dotted line has to be right up against that flat surface. Any other scenario is gonna be washer method. Oh, the second issue is a lot of students want to do this because this is a way that we find area, right? Area, we do top minus bottom for the shaded region, but we don't do that for washer method. For washer method, we never connect between the shaded regions because if we're trying to find the radius, we got to involve the dotted line. Okay, it's like saying you're connecting between the two outer ring and then calling that the radius. Okay, we can't do that. So just make sure that for washer method that we never connect between the two shaded region and calling it, something that's like a radius big R or little r. We always have to include dotted line as you're building out the distance of your little r and big R. Okay, next page. Let me skip down to example 4 because I want to make sure that we do also the more difficult problems are the ones where you have a vertical axis and you have a horizontal radius and you got to spend the time to rewrite your equation. So let's do example 4 here. Now we're rotating about the line x equals -2. That's a vertical line there. So x equals -2 is a little bit off the grid here. So I'm going to draw that in here. So anytime we have a vertical axis we know our radius is going to be horizontal. And because our radius is horizontal, we know that any horizontal length, whether it's radius or height of a rectangle, we have to make sure we spend the time to rewrite our equations, right? So, but first off, we know if there's an obvious gap. This is going to definitely be washer method. We need two radius. So starting on the axis of revolution, I'm going to extend to the furthest boundary, and that's going to be my big R of y. I'm going to pick a spot on my axis and extend to the closer of the two boundaries, and that's going to be my little r. So horizontal radius, we know these equations are not going to be a good fit for our formula, so we have to spend the time to rewrite these equations. So y equals x squared. I can adjust this to now be what? If I want to solve for x, x equals what? X equals square root of y. And then for the y equals square root of x, if I solve for x, x equals what? X equals y squared. So x equals root of y is going to be the curve that's further away. We'll use that for big R. And then x equals y squared is the curve that's closer to the axis. So we'll use that for little r. And then we're stacking these circular rings from the lowest to the highest y values. So our bounds will be from where to where? Also 0 to 1. But not because we're looking at the x values, but because we're looking at the y values. Right. Okay. Big radius, big R. Right minus left. The right endpoint of my big radius is sitting on the root y, minus the left endpoint is sitting at the -2, so it's going to be root y minus what? Yeah, so we got to be careful here. We have the negative from the formula, right minus left, and there's also a negative from the axis, so the two negatives will become positive. Okay, little radius, right minus left. The right endpoint of little radius is sitting on the y squared, minus left endpoint, also sitting on the axis, so minus a -2. Okay, we have everything that we need to build out our volume by our integral formula, or integral for washer method. So we'll go from 0 to 1. Big radius, quantity squared, minus little radius, quantity squared. Make sure that as you do your washer method that you're squaring your radius separately. We don't want to do big R minus little r and then squaring it just once. Okay, that's different. Okay, so make sure that you're doing big R quantity squared and separately minus little r quantity squared. Okay, in your calculator, you're going to use what variable? X. Okay. So under y1, I'll use root x plus 2. Y2, I'll do x squared plus 2. Let's see if this can convert to a fractional value. It doesn't, so we'll just attach pi after 3 decimal places. So we'll do 1.633 pi cubic units. Okay, let's go to page 15. Practice some more variations of washer method. Okay, try part A. Identify your shader region, identify your axis of revolution, decide whether this is, convince yourself that whether this is this method or washer method. If it's washer method, you want to make sure you can draw in your 2 radius. Now, on the quiz, I will draw the diagram for you, but I may not have all these numbers set out for you. So you may have to solve it either by hand, or you may have to plug in the calculator and find those intersections yourself to identify the bounds. So in this case, this is not too bad for you to solve by hand. Root x minus 1 equals to 1. I can solve for x and see that x equals 4. But you can also graph the 2 functions and then do intersection feature and find that intersection, convince yourself that's also 4 in your calculator. So our axis is all the way down at y equals -3. We want to extend from the dotted line to our 2 boundaries. Big R will extend all the way to the y equals 1. And little r will extend from the axis to the root x minus 1. We do top minus bottom for both. Set up your volume formula and make the calculator do the rest for you.
Here we supposed to sketch them.
For part B, say it again.
Are we supposed to sketch the line?
Yeah, the line isn't drawn for you. You have to draw it in. Yeah. Any questions with 1A? Right. Part B is a vertical axis revolution, which means a horizontal radius, which means the equations need to be rewritten, right? The form that's given to you is good for top minus bottom, but it's not going to be good for right minus left. Right? But part B is also washer method because there's an obvious gap between your axis and your shaded region. So now the radical function needs to be rewritten as x equals. So it will be written as x equals quantity y plus 1 squared. The other boundary is the x-axis, y-axis, which is x equals 0. And then your axis of revolution is x equals -1. So you look at all your equations you're using, they all have that setup of x equals, right? That x equals, and x equals. So those are indications that you have your equations ready to be used for washer method. Well, at least for right minus left. Okay, you're stacking these circular rings from the lowest to the highest y value. Lowest y value is -1, highest y value is +1.
This one, like, what is it? What's the radius look like?
Um, not sure what you mean.
Like it says for a horizontal radius for right to left, right? So. I mean, for the line is vertical, so that's how we. How-
Yeah. So this object is rotating around this way. So we're getting these circular rings that are horizontal, and so all your radius is going to be horizontal as well. Yeah, that makes sense. Any questions with 1A or 1B? Okay, try number 2. Oh, keep in mind that whenever you're dealing with bounds, your bounds is just for the shaded region. Okay, doesn't matter how far away your axis of revolution is. That's never going to play a role in your bounds. Okay, so some students feel like, oh wait, my axis is all the way over here. I need to factor that in if I want to do my bounds. Your bounds is just for your shaded region. That's it. Okay. And also for this diagram, the X and Y axis are just there for reference. It's not really part of the boundary. Okay, this method or washer method? Washer, yeah. It's touching, but it's not good enough, right? It's not up against the flat surface. There's all these gaps here that's going to account for us having to involve washer method. But this is top minus bottom, so we can hold on to the functions that's given to us. Big radius will extend from the axis all the way to the furthest boundary. And little radius will extend to the curve. Okay. Your bounds is going to be as far left and far right as the intersections between the curve and the line. You could either graph the two functions, look for those intersections, but I think it's easy enough to set them equal to each other. top minus bottom. The top is sitting at the 3. The bottom is sitting at the -2. So 3 minus -2. Okay, little radius, top minus bottom. 3 minus parentheses. I think it's always a good idea to protect your left or your bottom function with a set of parentheses so you remember to distribute that negative through. So volume equals pi integral from -√5 to √5, big radius squared minus little radius squared. Okay, part B. Now we're taking the shaded region and rotating about the line y equals -2. What do you notice for part B here?
Like the other method.
Okay, yes, this is this method, right? Because now your dotted line is right up against the flat surface of a shaded region. There is no gap. This is going to be this method. So this method only requires one radius. There's no hole to subtract out. Okay, your bounds are the same. You just have to draw in your radius and do top minus bottom. Okay, so a couple of skills that want to make sure that we are gathering as we move towards getting ready for the quiz. One is I'll draw the diagram for you, but a lot of times you have to find the intersections yourself. So know how to find those intersections using your calculator. Be comfortable with adjusting your windows, whatever it takes to get to your intersections. Sometimes you can solve it by hand. Other times you have to look for the intersections on your own. Know how to identify between this method and washer method. It's up to that dotted line in relation to your shader region. Okay, that's how we tell. And then third, make sure that if you see a vertical axis, which means a horizontal radius, that you're taking the time to rewrite your equation because your equation is largely not going to be in the correct form for right minus left. If you can do those three things, then you're on a good track to do well on the quiz next week. Okay, so your homework is going to be a combination of Monday and Tuesday from your calendar. So from your textbook problems, page 592 to 596, 5, 7, and 8 will be this method, 10, 47, 49 will be wash method, and then AP practice 8.2, 1 to 10. We have one more topic to go over, and that's volume by cross section. But if you feel good with this method, washer method, and knowing your vertical and horizontal radius, we're just going to be doing a slight adjustment with cross sections. But it does require us to memorize a couple of formulas, so we will talk about that tomorrow. But after tomorrow, we can go begin our quiz review. So we'll do quiz review Thursday and Friday. Then Monday, I do need to start the next topic, reviewing FRQs, but your quiz will be next Tuesday. All right, can we meet your phones?
Okay. So answering some of these questions for fun. I don't think I got any of them right.